Hey everyone, so this video is about a simple pendulum and solving it a different way than we did in problem set 47. In that problem set, we applied an approximation to the differential equation to try to simplify it. And in this video, we're going to apply a different approximation to try to solve it a different way. And arguably, this way is better, and we can talk about some of the ways it's better or worse than the small angle approximation. But the differential equation that we're working with here looks like this. So we have theta double dot is equal to minus g over L sine theta. That's the basic equation that governs the dynamics of our simple pendulum. And it's really hard. You can solve this analytically, but it's really complicated. And all that complication isn't super illuminating. So what we want to do is make it a little bit easier on ourselves. And we're going to do that by solving it numerically. And what that means, I'll try to help explain in this video. That's kind of what this video is for. But it is an approximate solution. So the basic thing we're going to do here is we're going to set up a system of equations and solve those iteratively. So a numerical solution is an iterative solution. I'll write that down. So the basic premise of what we're going to be doing is we're going to look at really short time steps, assume that this thing, g over L sine theta, is constant for our little small time step, and then update the value of theta at each time step, assuming that sine theta is constant. Sine theta isn't constant, of course. As time increases here, the value of theta changes, and therefore the value of sine theta changes. But that's the approximation that we're making. And we'll see how good or bad it is once we get to the end. Okay, so the mechanics of this. What we have is a second order differential equation. So a second order differential equation is one that has a second derivative in it as the highest order derivative. I'm trying to write derivative. No, I'm trying to write differential equation. Yeah, second order differential equation. So that's this equation up here. But we want to split that turn this into two first order differential equations for reasons that will become clear later. So a first order differential equation is one that has a first derivative as the higher order derivative in it. So what we're going to do is we're going to define omega. So omega, just the rate of change of theta. So that is theta dot, the time rate of change of theta, is equal to omega. So omega now becomes another variable in our system that we're going to work with and update at each time step. But if we define omega, what we just wrote down, this is one of our first order differential equations, That's one of our first order equations. And now we can write our original differential equation as a first order differential equation too. Instead of being theta double dot, it's just omega dot equals minus g over L sine theta. Okay, so we have now, this is our other first order differential equation. Okay, so we turned a second order differential equation into two first order differential equations. And the reason why we want to do that is because the basic premise of what we're doing here is we're taking these equations and we're just kind of treating them as though like they're little fractions, and we're going to treat them algebraically. So really we have two equations here that we're looking at. Basically what we're saying is that we're taking, I'll call this equation 1 and equation 2. Let me start with equation 2. So equation 2 says that omega dot equals minus g over L sine theta. So what's omega dot? That's the rate of change of omega. So that is delta omega over delta t equals minus g over L sine theta. So what we're doing is we're saying let delta t be a finite value. Then delta omega is a finite value too. Instead of being a derivative, now we just have this ratio of finite values. As delta t gets smaller and smaller, we'll get that derivative back and we'll get an exact value. But what we're going to say is that this is now some finite value, finite non-zero value. And so is delta omega. And for some delta t, for our delta t, this is constant. That's not true. That's not actually true. But if delta t is small enough, it's not that bad of an approximation. But that's the basic premise we're doing here. And then if we do that, it's sort of a simple equation to see how omega changes in this time. Because I can rearrange some stuff here. So if I rearrange stuff, I can see that the change in omega is just minus g over L sine theta times delta t. But delta omega is just whatever the final omega is at the end of this time minus the initial omega at the beginning of this time. So I can write at the end of this time, the final value of omega is omega I minus the change in omega, or plus the change in omega, I guess, which is minus g over L sine theta times delta t. That's something that we can work with. All we're saying is that this is some value that we can calculate based on the value of theta at the beginning of our time step times however big our delta t is. And then we just have to know what the value of omega was at the beginning of our time. Similarly, looking back at our equation 1 here, we can apply similar logic. And it's a little bit less complicated here, but basically the same idea, where theta dot equals omega. And that's equal to delta theta over delta t. So I can, by the same process, say delta theta equals omega delta t. So that's the final value of theta at the end of the time step minus the original value of theta at the beginning of the time step. And so theta final at the end of our time step is equal to theta I at the beginning of our time step plus omega delta t. These are our two equations that we're going to use iteratively. So the basic idea is we're going to start with some initial conditions for theta and omega. That's going to be our initial theta I and omega I. And then we're going to update the value of theta and omega using small values for delta t, and just do that a bunch of times to get theta and omega as functions of time. It sounds complicated. In practice, it's not that complicated. And I want to walk you through a couple of steps here to show you what that looks like. Okay, so I've got a clean sheet here. Here are our two equations that we're going to use to do this iterative process. I'm going to do a couple by hand just to show you the way the process goes, and then I'm going to transfer over to Google Sheets and show you how to do it in Google Sheets, because using a computer for iterative processes is great. That's what computers are really for. So let's make a problem. So let's say that we have some pendulum, the pendulum has some mass, some length, and we have initial conditions. So let's say we release the pendulum from some angle. I'll call that theta naught, and let's say that's pi over 4. So that's 45 degrees. So we release the pendulum from 45 degrees from from 0, its equilibrium position, and we release it from rest. So the initial value of omega is 0. The units we're using here are radians, so this is radians, and that's radians per second. Okay, so how do we do this? We also need to choose a time step. The smaller our time step is, the more accurate this will be. You don't necessarily know how small your time step needs to be to make it accurate before you start. I'm just going to choose a time step that seems reasonably small. We'll see how it works out. Once we get into sheets and start working with stuff, it'll be easy to manipulate that value. But let's just choose a time step of 0.1 seconds. So every time we iterate, we're going to update the time by 0.1 seconds. Okay, so how do we do this? So let's say I want to find omega 1, which will be my first calculated value of omega. So the way I'm going to do that is I'm going to take the previous omega, which will be the initial value of omega at the beginning of my first time step, whereas omega 1 is the value of omega at the end of my first time step. So I've got my initial omega, and then I subtract the value of g over L sine, and now sine would be theta naught here too. That's the value of theta that I have, and I'm just assuming that sine theta stays constant over this time step, times the time step delta t. So omega naught is 0. So this is 0 minus g over L sine pi over 4 times 0.1. And if you work that out, you get minus 0.693 radians per second. That's some number. That's an approximate number too. I just rounded. And now I got to update theta. So theta at the end of this first time step will be equal to the initial theta plus omega times delta t. I could choose to use omega naught here. I'm going to choose to use omega 1. There's not necessarily a great reason for that, but that's how I'm going to do it. So I'm going to choose omega 1, assuming that this is like the best version of omega that I know at this point. And I'm assuming that that's constant over my time step. So I'm multiplying that by delta t here. So if I do that, I get, that's pi over 4 minus 0.693 times 0.0, not 0.01, 0.1. And that, if you work it out, is equal to 0.716 radians, a little bit less than pi over 4. Okay, so now these are the values at time equals 0.1 seconds. Our initial values were the values at time equals 0 seconds. So if I do this again, I should get the time, the values at time equals 0.2 seconds. So let's do one more just to see how it works. So let's keep going another step. And we're just going to do the same process, but we're just going to update the values. So now omega 2 will be equal to omega 1 minus g over L sine theta 1 times delta t. So we've just updated the values based on our last time step. So now the delta t is taking us from 0.1 seconds to 0.2 seconds. So our initial values in here are the theta and omega values at 0.1 seconds. You can work that out. If you work it out, I got minus 1.337 radians per second. And theta 2, so that's now theta 1 is the initial theta for this time step, plus omega 2 is our updated omega for this time step, times delta t. And if you work that out, you get 0.582 radians. So now these are the values at time equals 0.2 seconds. And we could just keep doing this forever, and we would have an approximate solution to the differential equation. We'd get we'd get data that would tell us functions for theta and omega, and we could plot those if we wanted to. So that's where we're going next here. I'm going to switch over to Sheets and show you how to do it in Sheets. One last thing, what we're doing here is called Euler's method for solving. So this is called Euler's method, and Euler is spelled E-U-L-E-R. You'll see Euler's name all over the place in math. He did a lot of stuff. And it's not necessarily the best way to solve differential equations. You can see that the approximation that we're making is we're assuming that these quantities, this quantity right here, and this quantity, and this quantity, we're assuming those are constant for the time step when they're not. You might be able to make better approximations of their values during the time steps. Like say maybe you would use the average value of theta for a time step, or the average value of omega for a time step. But Euler's method is pretty straightforward, and that's what we'll use here. So now I want to show you how to do this many times, so you don't have to do it by hand. So I'm going to switch over to Google Sheets and show you how to do that. Okay, so here's a Sheets workbook. I've got it set up to hold some constants. So the constants I need here are G. I'm defining that as 9.81 meters per second squared. The length of the pendulum, I'm just using L equals 1. And I don't think I said that when I was working pencil and paper just then, but I was using length equals 1. The time step that we just decided on arbitrarily was 0.1 seconds. And the initial conditions we're working with are pi over 4 for the angle and 0 for the angular speed. Okay, so let's do this. So our first value, is times equal to 0. So we're going to start with the time column here having 0. Our initial omega is equal to our initial condition for omega. So that's, we're holding that in cell B8. So I'm going to put that in B8. And I'm not just putting in 0 here so we can have more flexibility and we can play around with different values, initial values for omega if we want. And then theta, our initial angle, is equal to what's in B7, that's pi over 4. Okay, so now we got to update all these things. And what Excel is really good at, or what Sheets is really good at, is formulas. So the next time that I want is the time just before this. So the time that's going to be next will be the time before plus delta t, or the time step. So this time here should be what came before, which is D2, plus the time step, which is in B4. I want that value to never update as I drag down the column. So I want to put in these dollar signs because that will freeze this constant. So if I now have this value, so this value is 0.1 because it's D2, which is the value in the cell above, plus the time step. When I drag this down the column now, I'll do a couple so you can see. It now increments by what's in B4 every time. So the way it works is this cell now D4 is D3 plus B4, then D4 plus B4 and so on. So if you don't put dollar signs when you drag down the column, the row number will increment. If you do put the dollar signs, then the row number doesn't increment and it stays constant, which is what we want. We just want the time step value to stay the same, but we want to reference the previous time when calculating the next time. So now let's do something similar for omega. So to update omega, we want to take the previous omega, so that in that case would be E2, so that's our initial omega, and then add the change in omega here, which is from our previous equation. So that's minus g over L. So g is in B2, and we want to make sure that that value stays frozen and doesn't, that row number doesn't change as we drag down the column. So that's B2 over L, which is B3. So that's B3, okay? And then we need to multiply by sine of theta. And the theta we're gonna use is the theta, the initial theta from the previous time step. So that is, we're using the theta that is in the time step above, so that's F2. So that's the previous theta, okay? And then we need to multiply by the time step. So the time step is in B4. Okay, so that gets us our omega. It's the same as what we calculated, just by hand. And to update the theta, now I do something similar. So to do this, I take the initial theta, so that's F2, and then I add the change in theta, which is omega times delta t. So the omega I'm using is the omega at this time step. I'm assuming that's the best value I've got. So I'm going to use that and assume it's constant. So that's the value in E3. Oh, excuse me, E3, times the time step, which is in B4, and I'm adding the dollar signs to freeze it. And now I've got my updated values. These are what we calculated to be the value of omega and theta at time equals 0.1. I can do the same thing for 0.2, but I don't have to do it by hand anymore. I can drag it. So if I drag these down to 0.2, it updates and I get approximately what I calculated before. I can drag down again and get something for 0.3 and so on. I can drag this down as much as I want, and I can do as many as I want at one time. So what I'm gonna do right here is I'm gonna do a bunch. So I'm gonna drag down, I don't know, a bunch of columns. Let's go 100 and see what happens. I think there's a faster way to do this, but I don't know how to do it if it's not the entire column. So I'm going to drag down. It takes a second to calculate, but now I've updated moving forward in time 0.1 seconds for every step for 10 seconds. I guess I can go all the way to 10 seconds here, just for, I don't know, no particular reason. But that's kind of cool. So I've got this numerical solution for theta as a function of time and omega as a function of time. I don't have an actual function. I don't have a continuous function, although now I can plot this and see what it looks like. So let me do that. So I'm going to take these and I'm going to insert a chart. Okay, there's a chart. All right, cool. So what I've got here is I've got the red is theta and the blue is omega. So you can see it's periodic motion, which is exactly what we'd expect. You could figure out the period from this just by kind of looking at where the motion repeats. And you can see the omega and theta are shifted from each other as we would expect to. So omega has its minima and maxima when theta hits 0. So that is, as the pendulum swings through its equilibrium position, it has the most speed. And then omega goes to 0 when theta is either at a crest or a trough. So when theta gets to the furthest angle that it gets to on either side, that's when omega goes to 0. So this kind of looks like how we would expect. And actually, it looks not super choppy. You can see a little bit of chop in the graph based on our choice of delta t. So if I blow this up, you can see that there are some jagged parts here, particularly when the functions change rapidly. So if you look at omega changing rapidly here, you can kind of see the jaggedness of it. If you want to eliminate that, which we might want to do, because the jaggedness is telling us that the function is changing pretty fast compared to our time step, we can just change the time step. So I can do that just by varying this constant. So if I turn it down, let's say I turn it down by a factor of 2 to 0.05. So now things look a lot smoother here. I've reduced how much total time my simulation covers now, because I just used a fixed number of cells. So I just have 100 cells, give or take. So then this time step times that many cells only gets me 5 seconds now rather than 10. But I could, in principle, just do this for another 100 cells and go to 10 seconds if I wanted to. I can make the time step bigger too and see what that looks like. So this was our original one. If I made the time step bigger, I would cover more time, but it looks even choppier. And there's probably some point at which the reliability of the solution is compromised if the time step gets big enough. If I make it really big, then that looks really choppy and really weird. So you can play around with the time step, you can play around with all the other parameters here, and kind of figure out what time step makes the most sense. But this is a numerical solution to the differential equation. From this, we could figure out a lot of stuff. We can do some interpretation. We could try to find the period and compare the period to the small angle approximations period, and analyze it that way. But that's the basic premise here. Sheets is a great tool for doing this. I think that's it. Next time we're in class, we'll work on another example, and we'll give you a chance to work on your own differential equation solver of this type on a different physical situation. So I hope that helps. And I look forward to talking to you all about this in class next time. Okay, bye.